Still guessing why your app launch feels slow? The cold start time is precisely the interval from the system creating the app process until the application renders the first frame. On Android, measure this duration using the command adb shell am_start-w, specifically analyzing the total time metric output. For iOS, utilize the Xcode Instruments time profiler, focusing intently on the dynamic linker loading phase and the main thread execution time before application did finish launching with options returns. Establish a strict performance budget, targeting under 500 milliseconds for the initial frame render. Differentiate cold, warm, and hot starts. Optimization efforts must primarily target the cold start scenario where the entire process requires initialization. Use the application startup metric available in Google Play Console and App Store Connect to monitor real-world performance data across diverse device types and operating system versions. Consistent, verifiable measurement is mandatory before implementing any optimization strategy. Optimize the initial window background to minimize perceived latency before the first activity layout is drawn. Implement a custom theme that sets the Android.window background attribute to a simple drawable or a solid color matching the splash screen design. This theme must be applied directly to the launching activity within the Android manifest.xml file. Strictly avoid using complex drawables or large bitmaps in the initial window background, as these significantly increase inflation time. Content providers initialize before application.onCreate executes and frequently introduce substantial overhead. Developers must strictly audit and disable any content providers not essential for immediate startup functionality. If a third-party library relies on a content provider for initialization, investigate alternatives such as manual initialization or leveraging the app startup library to manage component initialization on demand and off the critical path. The iOS cold start is heavily impacted by the dynamic linker, dialed, loading all required dynamic libraries, dylibs. Minimize the total number of dylibs linked to the main executable. Every dylib adds measurable overhead for verification and loading. Audit third-party dependencies and consolidate functionality where possible to reduce the dylib count below 60. Ensure that the double_data segment of the main executable is as small as possible because dialed must process all fix-ups within this segment synchronously. Avoid using Objective-C plus load methods. These execute synchronously during dylib loading before main is called, directly blocking the startup process. Instead, use plus initialize methods or manual initialization calls invoked later within the application lifecycle. Move all non-critical initialization code out of the application.onCreate method on Android or application did finish launching with options on iOS. Critical initialization includes only components strictly required for the first screen to function, such as core logging or crash reporting setup. Implement lazy initialization for components like analytics, database setup, or remote configuration fetching. On Android, utilize Kotlin's ByLazy delegate or custom property delegates to ensure resources are only allocated upon first access. On iOS, use Swift's lazy stored properties for the same effect. If initialization requires background processing, use dedicated background threads, coroutines, or async tasks immediately after the main activity is displayed, ensuring the main thread remains completely unblocked. Dependency injection frameworks frequently introduce significant startup overhead, especially those relying heavily on reflection or runtime processing. For Android, prefer compile-time DI solutions like Dagger or Hilt or Coin's KSP integration over older runtime reflection-based frameworks. Ensure that the DI graph construction is optimized. Large, complex graphs must be partitioned or initialized lazily. For iOS, if using frameworks like Swinject, verify that the container registration process is highly efficient. Minimize the number of eagerly instantiated singletons within the DI graph. Convert singletons to factory providers or lazy providers where possible to delay object creation until injection is explicitly required by a consuming component. The time taken to inflate the main activity layout directly impacts perceived startup speed. Reduce the depth and complexity of the initial view hierarchy. Deep nesting exceeding 10 levels exponentially increases layout calculation time. Use constraint layout on Android or Swift UI and Compose equivalents to flatten the hierarchy structure effectively. On Android, consider using view stub for views that are rarely visible or only needed later in the lifecycle. Pre-inflate complex layouts asynchronously using async layofficator or prefetching views on a background thread before the activity requires them. For iOS, ensure that XIBs or storyboards are minimal for the initial view controller, or transition entirely to programmatic user interface construction for maximum control over initialization order. Strictly enforce that no input-output operations, including disk reads, network calls, or database access, occur on the main thread during startup. On Android, enable strict mode in development builds to detect accidental disk or network access on the main thread and crash the application immediately upon violation. Use dispatch.global.async or similar concurrency primitives on iOS to offload heavy computations immediately. Database initialization, including schema migration checks, must be executed asynchronously off the main thread. If data is required immediately for display, load a cached placeholder or use a lightweight in-memory structure until the persistent store is fully ready. Use platform-specific profiling tools to pinpoint exact bottlenecks in execution. On Android, utilize Perfetto or Systrace to visualize thread activity, CPU usage, and input-output events during the startup phase. Look specifically for long, contiguous blocks of execution on the main thread without yielding control. On iOS, use Instruments Time Profiler to analyze the call stack during startup, specifically identifying functions consuming the most CPU time within the main function execution block. Focus optimization efforts exclusively on the top 10 functions identified by the profiler output. Iteratively measure startup time after each optimization step to confirm performance gains and prevent regressions from being introduced. Leverage platform deployment features to improve startup performance for end users immediately. On Android, generate and ship baseline profiles. These profiles inform the ahead-of-time compiler which code paths are critical during startup, resulting in optimized machine code execution. Integrate performance monitoring software development kits, such as Firebase Performance or custom solutions, to track startup metrics accurately in production environments. Set up automated alerts for performance regressions that exceed the established budget threshold. Utilize A/B testing to validate the impact of major startup optimizations on user engagement and retention metrics, confirming that faster launch times correlate directly with improved business outcomes.